Okay, welcome to the Applied Math Colloquium. Today we are delighted to have a former alum of the Applied Math Department here, Stephen Kissler, who is going to be giving a talk on something we all have been experiencing quite extensively in the last year. Stephen is, so he got his bachelor's degree here at Colorado back in 2013, a master's in 2014, and then got a Gates Cambridge fellowship and went off to Cambridge and got a degree in 2018 in the applied mathematics over there. He continued as a junior research fellow at Queen's College over in Cambridge and is now a postdoc in the Chan School of Public Health at Harvard. What can I say? He's been on quite a streak in the last year. Maybe I'm counting wrong here, but I see 10 publications in the last year since the pandemic started. So I've been quite busy, I can see. With that, I will turn it over to Stephen, who's going to share and tell us all about what he's been working on with regard to COVID. All right, Stephen.
Awesome. Thanks so much. I'll get my slides pulled up here. And while I do it, just wanted to say it's really an honor to be here. It's great to see many of you who I know. It's just really nice to be back. So thanks very much for the invitation. So today I would like to sort of give a brief overview of some of the projects that we've been involved in. It was a very generous introduction, and 10 publications makes it sound like a lot, but that was far from an individual effort. So it's really an honor to get to be really the spokesperson for a lot of these projects. So I've titled the talk SARS-CoV-2 Across Scales, really getting at 3 different geographical scales that we were interested in looking at as the pandemic sort of wore on. So to dive right in, there's 3 main themes that I'll be speaking about today. The first had to do with questions that we had very early in the pandemic that had to do with the long-term global spread of SARS-CoV-2. The second was looking at New York City in particular, looking at disparities in COVID-19 prevalence within the city. And then the last will bring us up to the present day, where we're looking at differences in viral trajectories of SARS-CoV-2 variants within the human body. Each of these drawing on different areas of mathematics. I like to say that I took the applied part of applied mathematics and really ran with it over the last few years. But I think there are some really interesting nuances of the mathematical side of things as well that hopefully we'll get a chance to discuss. So starting off with this first one, if you can, and it's not too uncomfortable, I'd like you to cast your minds back to where we were about a year ago. And it's hard to recall just how little we knew at the time about SARS-CoV-2. So we as epidemiologists, during my PhD, I did a lot of work on pandemic influenza and mathematical modeling of that. And so that's where I first got to know much of the epidemiological community. The thing we were really afraid of a year and a half ago was a flu pandemic. That was really what a lot of us were preparing for at the time. And so we had sort of these 2 respiratory pandemic paradigms in mind that were starting to inform how we were thinking about SARS-CoV-2 when it was first beginning to spread. So the first of those was influenza. On the top left here, I've depicted deaths in the United States from the 1918 flu pandemic. One of the things you'll see immediately is that it spread in 3 main waves. There was an initial spring wave that primarily just struck New York City. Sounds familiar. Then there was a fall and winter wave that was really most of the mortality was then. And then an additional wave in 1919. But it didn't end then. The 1918 flu continued mutating, but its descendants continued circulating all the way up until 1957, when it was then replaced in another pandemic by an H2N2 flu strain, which was then replaced by another pandemic in 1968 by an H3N2 strain. You'll see this resurgence of the 1918 H1N1 strain. We think that actually probably came from a laboratory accident where it escaped from the lab and started co-circulating with H3N2 until it was finally replaced in 2009. So we get these interesting dynamics where there's this influenza pandemic that causes multiple surges of infection. But then after the fact, it does this interesting thing where it enters into seasonal circulation as a wintertime respiratory virus. So that was one of the paradigms that we had in mind. The other had to do with coronaviruses. So SARS-CoV-1 broke out around 2003. It was first detected in China, caused a lot of infections, especially in Hong Kong. But in many ways, this was the pandemic that wasn't. It caused cases in a number of countries around the world, but by the end of 2004, it had effectively disappeared. So this was something that there was a lot of concern about, but it never really took hold. Um, it, I want to be very clear about the fact that that's probably because of the intense control measures that were put in place when it first spread. It didn't just die out of its own accord. There was a lot of effort to make sure that it didn't become a pandemic, but nevertheless, it didn't. And so we weren't really sure if coronaviruses could really cause pandemics on the scale or of the frequency that flu did. On the bottom right of this slide is what we know about, or what we knew prior to SARS-CoV-2 about the other common cold coronaviruses. So there are 4 other strains of coronavirus that circulate and cause the common cold. These are seasonal respiratory viruses that circulate in the winter. They have these names: OC43, NL63, 229E, and HKU1. And you can see that they co-circulate. They kind of come and go. But we didn't know an awful lot about these because, again, we've been spending so much time thinking about the flu. This common cold coronaviruses really don't, they can cause severe illness in some people who are immunocompromised or older sometimes, but usually they're not thought to be very severe viruses. So our attention hadn't really been paid to those coronaviruses prior to SARS-CoV-2. So that left us in an interesting spot where we had SARS-CoV-2 beginning to spread, and we needed to learn as much as we could, as quickly as we could, about coronaviruses. So one of our first efforts was just to try to understand how the common cold seasonal coronaviruses behave. What do they do? What are their specific dynamics? And then how can we apply those lessons to SARS-CoV-2? So in our first major effort during the pandemic, this was back in, this started actually end of January, beginning of February 2020. We looked at the spread of the beta coronaviruses. So 2 of those 4 strains that I mentioned on the previous slide are beta coronaviruses. The other 2 are alpha coronaviruses. And these 2, HKU1 and OC43, are the closest relatives to SARS-CoV-2 that are currently circulating. So we decided to take a look at them in particular. And we wanted to know just what are their epidemiological attributes. How transmissible are they? Do they interact with each other at all? Why do they spread in the winter? How long does immunity last? These kinds of things. So to begin to answer these questions, we relied on the old standard epidemiological model. This is something that many of you may have probably seen at this point. And so this type of model, what we call the SEIR model, forms the backbone of a lot of epidemiological modeling that has happened over the past century. The idea behind it is that you can categorize individuals in a population in terms of their epidemiological state, where they can be either susceptible to disease, they can be exposed but not yet infectious, they can then be infectious, and then they can recover. And the recovery state usually captures both people who have recovered and are then immune, or also people who have died from the disease. But in either case, they're not contributing to further transmission. So this gives us a framework where we can write out some differential equations to describe the rates at which people move between these compartments. So you become exposed at a rate beta multiplied by the number of people in the population who are infectious. So the more infectious people there are, the more likely you are to become infected. So that's this beta IS term. And then we can just follow it through. The other terms are relatively simple. There's just a constant rate of progressing to infectiousness and a constant rate of progressing to recovery. And that gives us the initial framework that we can work with. In this little inset plot right here, I've just shown sort of the, it's a schematic of the dynamics that you can expect from these types of equations. And they're interesting, but they're not that interesting. So on the vertical axis is the number of infected people. Horizontal axis is time. And essentially what you can get is this initial rate of exponential spread, and then it peaks and then declines at a slower rate, and then effectively disappears. But of course, this isn't sufficient to describe the dynamics that we're seeing over here on the left-hand side. We see these recurrent wintertime epidemics, so we need something else. Well, for the epidemics to recur, we think that there probably has to be some way for you to become susceptible again, even after you've been exposed. So we can introduce a new arrow here, which captures people going from the recovered state back to susceptible at some rate sigma. And I've updated the schematic now to show that you can still get this exponential rate of increase and the turnover. But now what we end up with is essentially a steady equilibrium state. We end up with an endemic disease, but again, not something that has these repeated wintertime epidemics. So to get that, we need yet something else, which we need is that we need this transmission constant, this infectiousness of the disease, to depend somehow on time. And this is actually pretty well experimentally verified as well. The idea behind this is that during different seasons, especially in temperate parts of the globe, people's behavior change. So you spend more time indoors in the winter. There are also weather factors that influence the ability of certain viruses to spread. This is, again, pretty well pinned down for the flu. Not so much so for coronaviruses, but if you allow this transmission constant to change over time, you can start getting these recurrent wintertime epidemics. And so those are the main updates that we needed to this SEIR model to begin to capture the dynamics that we were seeing with the common cold coronaviruses. The last thing we needed to do was to recognize that we're not just interested in one strain, but we're interested in two. That makes things somewhat more complex. But what we ended up doing was this. I wanted to highlight in red, this is just the same SEIR model that we had before. But now we've introduced a second strain. And the second strain, you can also become co-infected with the second strain. And when you're infected with one, your chances of getting infected by the second strain go down by this factor of chi. And so this gives us something that is now sufficient to explain seasonal recurrent wintertime dynamics of two different coronavirus strains. And so what this then becomes is just sort of a glorified parameter fitting problem. And so just using the standard tools of maximum likelihood with ordinary differential equations, we can fit this sort of model to the available data. So now I'm sorry for the slight color changes. I'm using a different version of this figure. But here again on the left is the same data that I was showing before in the solid curves, and then the simulated data after we fit the model parameters in the dashed lines. And you can see there's a pretty good fit between these two strains, between the data and the simulated trajectories. So what have we learned from this? Well, some of the things that come out of the model after we've fit it is that it seems like immunity to these common cold coronaviruses declines on average within a year or so. And this aligns actually with experimental evidence that was gathered previously, where people were actually intentionally reinfected with the same coronavirus strain that they had in the year previous. And it took about a year before they became susceptible again. The reproduction number, which is the number of people that an infectious person is expected to infect, varies quite a bit from around 2.2 in the winter to about 1.7 in the summer. And so that explains some of the variation in the virus's ability to spread between different times of year. And the last thing that I think is really interesting is that there's pretty clear evidence of cross immunity between these two strains. And you actually don't really need a model to suggest that this might be the case. You can see that when OC43 is really high, the incidence of HKU1 is relatively low, and vice versa. They sort of trade off from year after year. So this suggests that there's a lot of really interesting dynamics going on between the common cold coronaviruses. And now, of course, our interest is in SARS-CoV-2. So what happens when we put in yet another coronavirus strain here? So essentially, I mean, the mathematical idea behind this is really, we've already done all of the hard work. We just introduce a new strain on top of these two that are already circulating. And then we just see what happens. Again, at the beginning of the pandemic, we really didn't know a lot about SARS-CoV-2. We had some rough senses of the transmission parameters. But really what we were trying to do was ask ourselves, what happens when you vary these parameters within plausible ranges? What are the sorts of dynamics we can get out? How likely is it that we are going to see this endemic recurrence of SARS-CoV-2 over time? And so those are some of the questions we tried to ask with this model. I'm going to highlight three of the scenarios here that we looked into. The first was if SARS-CoV-2 has a relatively short duration of immunity that's on par with the common cold coronaviruses. And here you get something that looks a lot like the flu paradigm, where you have a major pandemic. It disappears for a little while, and then it starts causing these seasonal wintertime outbreaks year after year. If immunity lasts a little bit longer, which we might have reason to believe that it does, given some information that we have from SARS-CoV-1, then you end up with basically what you would expect, where rather than seasonal annual wintertime epidemics, you can get these biannual, every other year outbreaks of SARS-CoV-2. But I think the most interesting scenario that we looked at was this one. In these previous two scenarios, we didn't include any cross immunity from the common cold coronaviruses towards SARS-CoV-2, but that's what we did in this last one. So this is 2-year immunity with cross immunity coming from the common cold coronaviruses. And here we end up with something that's interesting. I think this is the one that actually most closely seems to match what we've seen already, where we have sort of a summer surge of infection followed by a wintertime larger surge in infection. Then interestingly, it dies away for a number of years in between before it finally resurges. And in those intervening years, it's essentially being kept suppressed by the circulation of OC43 and HKU1. You don't need the cross immunity to be very high to see this. And so even if there's just a small amount of cross immunity, we might expect this period of time with low SARS-CoV-2 circulation, but then we could be in for a resurgence a couple of years later. So really what this is underscoring is that I think we're going to need to maintain surveillance for SARS-CoV-2, even if it looks like in the coming months and years, like we've largely got it under control. It doesn't necessarily mean that we're out of the woods, which is an unfortunate place to end this first part of the talk. But that was one of the things that our first efforts helped to sort of clarify, and to clarify what sorts of information we still needed to distinguish between these different trajectories. So I will move on now to the second effort. So this was sort of as spring was turning summer, and it was becoming clearer and clearer that there's a very clear story of SARS-CoV-2 affecting different communities in profoundly different ways. Really stark racial and ethnic socioeconomic disparities that manifest as geographic disparities in the outcomes from COVID-19. So some of our initial thinking was really grounded in this work and others like it. So there was some work that came out that was describing basically just the differences in hospitalizations and deaths in New York City by New York City borough. And there's some really profound differences. You can see in the Bronx that both hospitalizations and deaths were on the order of, the rates were on the order of twice as high as they were in Manhattan. And this raises an interesting question, which is that, are these differences due to just differences in disease outcomes? Is it because people are getting infected in these boroughs and have less access to care? They have higher rates of comorbidities, and therefore they're getting hospitalized and dying at higher rates? Or does this reflect differences in how much disease there is, how much infection is actually transmitting? And it's important to distinguish between those two things because you'll want to intervene in very different ways depending on which of those is the key driver. If it's just a matter of poor outcomes given illness, then we need to think about our health infrastructure. We need to think about getting people access to care quickly. But if it is in fact related to differences in the rates of infection, then that suggests that infection control might actually be a way of managing some of these huge disparities in infectious in COVID-19 outcomes. So there are a couple of real challenges with this, though, especially at this phase of the pandemic. So on the right-hand side, I've highlighted the New York City's estimates of the cases per 1,000 people across the city. So you could look at this and you might say, well, that's pretty clear. There are absolutely differences in the rates of disease between these different boroughs. But when looking at this, we need to bear in mind that at this stage of the pandemic, almost all of the testing was being done in severely ill patients. New York City was pretty well overwhelmed. They weren't doing asymptomatic testing. They were hardly doing minimally symptomatic testing. So most of the people who were getting tested were people who were already really poorly off as it was. So these pictures could have been pretty well confounded by that first hypothesis that basically just people were getting sicker. And that was driving these differences in testing and the differences in positivity that we were seeing between the different boroughs. So we have a couple of challenges here to try to answer this question. So first, how do we measure prevalence when the case counts themselves, when the data we have is not really representative of the population we want to measure? And then an additional complexity is that the tests themselves really aren't perfect. If you are negative for SARS-CoV-2, you still may well be positive. There's a relatively high rate of false negatives for SARS-CoV-2 PCR tests. So how do we incorporate all of this to try to get a sense of what's going on in New York City? Well, to partially address the first issue about the non-representativeness of the data, we were able to rely on this really interesting work that was being done by a collaboration between different hospitals in New York City. So there was only one population in the city at the time that was being screened for SARS-CoV-2, regardless of their COVID-19 status, and that was pregnant women who were being admitted to hospital for labor and delivery. So all of these women were universally getting SARS-CoV-2 test. And that allowed us to get sort of a first estimate of how much SARS-CoV-2 there was in this population that wasn't biased by people needing to show symptoms in order to get a test. So I'm just highlighting this initial figure from one of the studies. I won't go into this too much, but one of the things that they found that was really surprising was the rate of asymptomatic illness at the time. But this gave us sort of the first sense of how much SARS-CoV-2 there was at the time. But we still haven't resolved the second issue, which is that what do we do when the tests themselves are imperfect? To deal with this, we relied on some work that was led by Dan Larimore, also an applied math alum and now a CU Boulder member. And so we were looking at some Bayesian statistics here to try to understand sort of how can you extrapolate from an imperfect sample to the population prevalence of some disease. So to illustrate the idea here, I've depicted 20 people, 3 of whom test positive for SARS-CoV-2. Given statistics, anybody can divide 3 by 20 and get a point estimate for what the population prevalence is. If we want to be a little bit more sophisticated, we can assign some binomial probability to this and figure out what the population prevalence might be, given that this is just a sample of 20 from a population that we're trying to extrapolate to. But then the question is, what do we do when there's a chance that there are some other people who have been infected who are positive, who actually are infected, but came up negative on the test? So that's not too difficult to incorporate. We can incorporate the known rates of false negatives and false positives within these binomial probabilities. And then with through invoking Sir Thomas Bayes, then we can sort of flip the probability around, get the population prevalence over here. And effectively what all of this does is it shifts this distribution to the right a little bit. Now here I'm only paying attention to the false negatives because the rate of false positives for PCR tests is really low. That changes if you're looking at things like serological tests to try to measure past exposures, but I won't be going into that in much depth here. But effectively, if you're worried about false negatives, then that has the effect of shifting this posterior estimate of the distribution towards the right. And we can now do this in a statistically rigorous fashion to try to get an estimate of how much SARS-CoV-2 is circulating in any given population, given these limited samples and given an imperfect test. If you want to play around with this, take a look at that URL. It's actually a lot of fun. You can put in your own testing attributes and see some interesting things. So what happens when we apply this to New York City, right? So we first actually saw a picture very much like the one we saw before, where the differences in the estimated prevalence tracked very well with the differences in hospitalizations and deaths by New York City borough. And again, that's not terribly surprising, but it's useful to know. But we didn't want to stop there. We wanted to know what was driving these differences in prevalence as well. So some of the members of our group have been really involved in looking at human mobility and using mobile phones as a way of measuring how people move from place to place. One of the really striking things about this pandemic is that mobility really plummeted in the early days of the pandemic. So here on the bottom, I'm depicting some data from Facebook's Data for Good program, where they were making some of these data available for researchers. And there's about a 40% decline in movements, overall bulk movements, from the pre-pandemic period during the early phase of the pandemic. So the study period we were looking at here was between these 2 vertical bars. And so mobility had declined quite a bit at that point. It was pretty constant across that time period. So one of the hypotheses that we had was that maybe these differences in prevalence reflect the fact that essentially some of these communities have higher numbers of essential workers, people who couldn't stay home from work and couldn't protect themselves from getting infected. So one of the valuable things about this particular mobility data set is that it allows you to take a look at mobility patterns at different times of day. So we were able to measure the number of movements out of boroughs in the morning and the number of movements back into boroughs in the evening. And we could use that as a proxy for the amount of commuting that was happening. And we could measure the declines in these commuting style movements to see which boroughs had the greatest declines in commuting and whether a large decline in commuting style movements reflected a relatively low prevalence and vice versa. So it does, they match up remarkably well here, where I've inverted the color scale on the right-hand side so that it's a little bit easier to match up. But basically the idea here is that in Manhattan, so up here, people were able to stay home from work. The commuting style movements really plummeted on the order of 70%. And they also had a much lower prevalence of disease. Whereas in South Queens, the opposite is true. Many more people were still sort of doing these commuting style movements, and that reflected a much higher prevalence. So again, it's dangerous to draw too much out of these correlative type studies, but I think what it was really pointing towards is that there's this mounting evidence that essential workers are at higher risk of acquiring SARS-CoV-2. And so that was again pointing towards a way of intervening, that maybe providing personal protective equipment, allowing paid time off of work, these kinds of things could be really important for reducing these downstream outcomes of higher rates of mortality and hospitalizations. So the last thing that I want to get into is bringing us up to the present day, really, which is looking at the viral dynamics of SARS-CoV-2 variants within the human body. So we've been hearing a lot about variants emerging over the past couple of months, and they're definitely alarming in terms, there's, I feel like we spent a long time early in the pandemic trying to explain why mutations were not particularly scary in SARS-CoV-2, but now we certainly have some mutations that have allowed for new gains of function, essentially, where some variants are able to more easily evade the immune system. Other variants are more infectious. Some are some combination of the two. Some are cause more virulent disease. And so we're really trying to pay close attention to these and to try to understand what exactly it is that makes them do what they do. So for this project, we focused in particular on the B117 variant, which is the variant that was first detected in the UK. And this is one of the variants that the main thing about it seems to be that it's more transmissible. It spreads more easily. Recent evidence suggests that it also causes more severe illness, but the transmissibility was really the thing that first emerged as the real thing that was alarming. So there was this really nice study by Nick Davies and colleagues out of the London School of Hygiene and Tropical Medicine that was looking at, again, an epidemiological model, a lot like the one that I introduced during the early slides, to try to compare different hypotheses for why B117 was spreading more easily in the population. So they generated models that encapsulated these different hypotheses and fit them to the epidemiological data that was available from the UK at the time. They tried a bunch of different hypotheses, but the two that seemed the most consistent with the data was first, this increased transmissibility, where here this means an increased chance of infection for a given contact. And there's good reason microbiologically for us to believe that this is the case as well. There are some mutations in the B117 variant that are known to enhance its ability to bind to the ACE2 receptors in the lung. So you can imagine that if you're exposed to the virus, it's just more likely that it's going to invade. I've highlighted some of those mutations here in the graphic on the bottom left. So that was pretty clear. And it seemed like a lot of the conversation was sort of moving that direction, that was really sufficient to explain all of the surges of infection of B117 that we were seeing. But one of the other hypotheses that they raised that was equally consistent with the data was the chance that there might be an increased duration of infectiousness as well. So of course, even if your probability of acquiring infection isn't any different given an exposure, if you're infectious for longer, then you're going to have more contacts on average, and that's going to allow the virus to spread more easily as well. So we wanted to examine this possibility, if B117 might also be associated with an increased duration of infectiousness. Now, there are a couple of ways that you can do this. One way would be to do really rigorous contact tracing in a large population and to try to compare whether people who have been infected with B117 actually do infect people at later stages of their infection than people with non-B117 types of infection. That's a very difficult thing to do. You need a lot of sequencing power, you need to have very good contact tracing, and you need to have large samples because we don't imagine that these differences in the duration of infectiousness are particularly big. So we decided that we would look at it from a different perspective, which was looking at the actual viral trajectories within individual people who were infected with B117 and non-B117 variants. So these data come from, they asked us to refer to them as a professional sports league. And these come from both players and staff and vendors and other affiliates, I think including family members, who were enrolled in their infection control program. So essentially, this league was testing all of these people daily or as frequently as they could for SARS-CoV-2. And that allowed them to keep a control of epidemics that might be spreading. But what it also did was produced this incredibly rich data set capturing viral trajectories within the body over time. So within this cohort that they were looking at, they had 65 participants who they found novel infections in, 58 of which had non-B117 infections and 7 had B117. So small sample size alert for all you statisticians in the audience. There are only 7 of these B117 cases that we're looking at, but I still think there's reason to believe that, well, I'll talk about it in a moment when we look at the statistical fitting procedure. So the idea here is that when you get a PCR test, normally what we hear back is just a positive or a negative. Do you have SARS-CoV-2 or not? But on the back end, depending on the type of test, you can actually get a lot more information than that. So the way PCR works is you get a little bit of virus if you're infected on the nasal swab, and then that goes to the PCR machine. I'm sorry if there are any microbiologists out there for grossly misrepresenting your field. But the idea is that the machine goes through these cycles that amplifies the virus by essentially doubling it until you finally get to a threshold where you can detect it. And so that's really useful because if you have to do that amplification cycle over and over and over again, then you probably didn't have much virus to start off with. Whereas if you very quickly detect a virus, then you might have had a lot of virus in that initial sample. So what we call that is the cycle threshold. The cycle threshold is the number of PCR cycles that you need to first detect the virus in a sample. And so that's inversely related to the log2 viral concentration that was on the initial swab. And so what we can do then is measure the CT value, and we can see how infection, the viral concentration is increasing and decreasing over time. So since the CT value is related to the log viral concentration, if we see a linear increase and a linear decrease in the viral load, then that corresponds to an exponential increase and an exponential decrease in the actual viral concentration. So really that's what we're after here. So on the right-hand side of this slide, depicting some of the data that we had available. And the idea is we want to know basically how long do these infections last? Well, it turns out that's a little bit of a tricky problem. You could imagine just measuring the time from the first positive test to the last positive test. But that's tricky, especially in the case of this blue one, for example, where this person seems to have largely cleared their infection. But there's this long chatter of positive tests at the end of their infection, which probably don't correspond to actual viable infectious virus. This is something that we've seen. It's really a key attribute of SARS-CoV-2. So really, we don't want to measure these chatter phases. We really want to know just sort of what's happening with this sort of robust middle of infection. To do that, we need a mathematical model. So what we did here is actually a really straightforward model. It's just a piecewise linear thing with 3 control points. And these control points correspond to the initiation of the detectability of the infection. Then it reaches a peak viral load, and then it decays to some clearance time, and then just stays there. And so we force these first and last control points to be fixed on the horizontal axis, and the peak CT value can sort of go around anywhere it wants to in between. And we can use, again, some Bayesian statistics. We're using MCMC model fitting procedure here to try to understand where these things sit. In particular, we were using a hierarchical Bayesian model, where first we drew proposed viral, in this case, viral concentrations from the population mean. And then from there, we drew the individual value. And by sort of refining this procedure over time, we were able to refine individual level fits, but that also informed what this population mean was. For the viral concentration, the peak viral concentration, we can do the same thing for the horizontal position of the onset of infection and the clearance time of infection. So it's really nice because that allows us to then compare these population means between the B117 infected people and the non-B117 infected people. So what do we find? Well, in terms of the difference between the peak viral load, essentially nothing. There is really no discernible difference between the peak viral concentration between B117 and non-B117 infected people. This is useful to know because another way that B117 could be more infectious on a per contact basis is if you're just producing more virus. Again, we can't eliminate that hypothesis, but here it doesn't really seem to be borne out by the data that we have. Things begin to look different when we take a look at the differences in the proliferation and the clearance times of infection. So here, there seems to be a bit of a shift with the amount of time that it takes the viral load to reach its peak. It's about 2 days for the non-B117 and about 5 days for the B117. I should say that here on these bars, I'm just depicting the mean of these distributions and then the 90% credible intervals underneath. A similar thing happens with the clearance time, where for the clearance time, we have about a clearance time of about 6.2 days for non-B117 and about 8 days for B117. When you put these together for the total duration of infection, you get something that that just begins to separate a little bit, where we have about 8 days for the total duration of non-B117 and 13 days for the duration of the B117 infection. So if we can depict these together on a viral trajectory, where the lines here are the mean viral trajectory, and then the 90% credible intervals here for the envelopes where those trajectories are expected to sit. You can see that the B117 trajectories are, they're starting to push a little bit longer than the non-B117 types. Of course, there's a lot of overlap. So So we can't say anything super definitive about this, but I can say that we did quite a few sensitivity analyses and tried different priors and different sorts of things to try to understand if this was some artifact. And it does still seem to be borne out more or less no matter what we do. So clearly the take-home message from this is that we need more data. But I think that the important thing about this is that it at least puts back on the table the idea that this increased duration of infectiousness could be something we need to pay attention to. And again, that could be important because it again just changes the way that you would want to intervene. If the virus is just more infectious, then that would imply that infection control measures, things like the recent suggestions to maybe double mask or really be like more vigilant about physical distancing could be important. But if in fact the duration of infection is longer, then we need to revisit isolation protocols. How long does a person need to remain isolated after infection to prevent from spreading infection onward? So all of this is things that we need to learn more about, but hopefully we'll have a lot more clarity on this before too long. So that more or less sums up some of the work that we've been involved in. There are a lot of other interesting things that we've been working on. I saw that Kate is on the call as well. She led some really exceptional work on vaccine prioritization recently that I had the privilege of being a part of, and so there's been a lot of really interesting work, and much of it comes right back to CU as well. And so I think the first thing that I wanted to mention is just that I've been really impressed by how mathematics has improved our understanding of COVID-19. I know that a lot of the sort of conclusions that I made during each of these sections of the talk had to do with things that were maybe not especially unexpected. But a lot of that happens in hindsight. As we were learning about this on the fly, there was a lot of clarity that mathematics helped to provide that I don't think we would have been able to get otherwise. It helped us sort of see more deeply into the data that was available, and crucially to understand what data we still needed to collect to get a better understanding of SARS-CoV-2. Pretty remarkable collaboration between mathematicians, epidemiologists, virologists, physicians. It was it gave me the opportunity to reconnect with Professor Bortz earlier in the epidemic when we were thinking about sort of control measures at the state level and at the national scale. And really all of this work, as much of a role as mathematics has played, I think that the ties between the scientists has played a really important role as well. And I would love to find a way to sort of foster these going forward. It turns out that they're absolutely crucial during a crisis like this. And so I think this is something that we're going to have to really think about how to foster as we move on. And that brings me to the last thing is we've learned an awful lot from this pandemic, but one of my most frustrating experiences at the beginning of the pandemic was having these consistent senses of deja vu, that knowing that we must have run into these problems before with the 2009 pandemic, with other influenza pandemics, with different things that had circulated. And yet we were sort of continually surprised by things as well. And so I think that really forces us to think about sort of what have we learned and what are the things that we do want to take forward, and how do we want to keep that in our collective memory as scientists, as epidemiologists, as mathematicians. Because I think that will be really important, heaven forbid the next time one of these things comes along. So I think I will leave it at that for now. Thanks everyone for your attention. I want to highlight again, as I said, this is far from my own work. These were huge team efforts. I've highlighted sort of which projects each of these people were involved in. There are too many to name individually here, but here they all are. And it's been an absolute honor to be able to work alongside them and so many others who I wasn't able to acknowledge on this slide as well. So thanks very much for your attention. And I'd be happy to take any comments or questions.